Hi everyone, this is going to be a lesson about the substitution rule. I'll remind you that we've learned how to solve indefinite integrals and definite integrals, but actually there are a lot of integrals that we don't know how to solve yet. It depends on what type of function we're trying to integrate. And with derivatives, we had to talk about a lot of different rules, like the product rule, the quotient rule, the chain rule. And with integration, there are also a variety of rules. Some of them you won't see in this class. Some of them are saved for Calculus 2. But right now, the substitution rule, which we'll talk about today, is going to help us to solve some problems that we can't do until we have this rule. All right, so let's go ahead and look at it. Okay, so actually, before we look at the substitution rule, I'd like you to do a little warm-up problem. Actually, I've got a part A and a part B. So I'd like you to pause the video and try to solve these. All right, so you see I gave you one integral of each type. We have an indefinite integral and a definite integral. We talked about rules for these, so you should get 6x squared over 2 minus x plus c, and simplify the 6 over 2 to get 3x squared minus x plus c. So that's the answer to part A. It's the family of all antiderivatives of that function. Over here, this is a different type of integral, right? This is area under the curve, so we're expecting that the answer we get to this should just be a number. It should not involve any x's or c's. So I get 2x to the third over 3 plus the integral of 1 is going to be x. We'll put the 1 and the 0 out here so that in the next step, we're going to evaluate at 1, evaluate at 0, and let's see. 2 times 1 cubed over 3 plus 1 minus 2 times 0 cubed over 3 plus 0. Well, I guess 0 cubed is 0, and this whole term is just going to be 0 in this case. So what have we got? We have 2/3 plus 1. Answer is 5/3. All right, so those are the types of integrals that we've talked about in previous lessons. If you're not sure about these, if you had any trouble with these, maybe go back and review those videos before you watch the rest of this one, because now the problems are going to get harder. Okay, so we're going to have a new rule that helps us solve some problems. It's going to be called the substitution rule. But before we get to that, we have a couple of preliminary things to talk about. So I want to talk about something called differentials. So if y equals f of x, where f is a differentiable function, we say dy dx equals f prime of x. So we've been saying that for a while now, right? We've been saying that all semester. That's just the notation that we use for the derivative. We could either call it f prime of x, or we could call it dy over dx. So that sentence is not really anything new. But now we define the differential. We define the differential dy to be dy equals f prime of x dx. Where dx is an independent variable. So what's going on here? We have always had this notation dy over dx, and it kind of looks like a fraction, but we've always just kind of left it like that. Remember that when we first talked about the derivative earlier in the semester, we understood that the derivative represents slope. Slope can be thought of as change in y over change in x. Sometimes we write it as delta y over delta x. So this notation kind of made sense from that perspective. This is the first time, I believe this is the first time that we've taken that dy dx and actually broken it apart. And we just have a dy sitting here by itself, and the dx is over here by itself. And we've never really had a reason to do that before, but in this lesson, this is going to help us. So we define dy to equal this. When we say dx is an independent variable, we mean that dy depends on the right-hand side. Or, instead of what we just did, if we had du over dx equal to f prime of x, this is just a u instead of a y. It's just a different letter, and we can define the differential du to be f prime of x dx. All right, so same thing as above. But labeled du instead of dy. Okay? But the reason why I'm showing you this last one is because in this lesson, it's usually going to be du. It's just going to be labeled differently. You'll see why. So how does splitting up the dy dx and getting how does splitting up the du dx and getting a du by itself, how is that going to help us? Well, you'll see in a moment. Now, I think I've said a couple of times already that the substitution rule is going to be something that helps us solve some problems that we currently can't do. So let me show you what type of problem I've got in mind. So, question. What is the indefinite integral of this function? So don't answer this yet. We need to talk about it. How would we integrate something like this? I mean, let's say we know how to integrate 2x. I know how to integrate 1 plus x squared, but this square root here seems to be messing everything up. It's kind of like we have a function times a function, which looks like maybe if it were a derivative, we would think about the product rule. Actually, I think if this were a derivative, we would also need the chain rule, right? But it's not a derivative. We're not differentiating this. We're integrating this. So we need something that's kind of like the chain rule, but in reverse. We need a new strategy. We really can't do this yet using the things from previous lessons. All right, so this is going to be a trick that we use. And the trick is we introduce a new variable. U. And what I'm going to do for this problem is I'm going to let u equal 1 plus x squared. Now we'll talk about how did I know to let u equal that. You could see that 1 plus x squared is part of the original problem, but how did I know to make it that part of the problem in particular? We'll talk about that soon. But if I let u equal 1 plus x squared, let's see, what is this going to do for us? I mean, I guess I could substitute in u in place of 1 plus x squared. It's called the substitution rule, so you might think we're going to do something like that. Before we do that, though, before we do that, let's take what I just wrote and do d dx of both sides. All right, differentiate both sides with respect to x. The left side becomes du dx, and the right side becomes 2x. Aha, so notice that the thing that we're calling u appears in the original problem, and the thing that we're calling du dx also appears in the original problem, and that's what's going to be pretty convenient for us. In fact, we can do this differential trick that we mentioned above. So split this up to say du equals 2x dx. Just move the dx over, I guess. All right, so the problem that we're trying to solve looks like this. I'm just rewriting the problem. And in fact, I'm going to rewrite the problem in a slightly different way. Instead of having the 2x out front, I'm just going to rearrange it to have the 1 plus x squared square root part first, and then the 2x. All right, so you can see that what I just did here, that doesn't really change much. I just moved the 2x to the right. The reason I did this is because, look at this, we have a 2x dx, and above we just said 2x dx is du. So the idea is that we can substitute in du in place of this, and we can substitute something in here because u is 1 plus x squared. This can just be written as the square root of u. So what this does is it transforms the problem into a smaller problem. Look at that. So we had a complicated problem in terms of x, and we turned it into a simple problem in terms of u. And by making this substitution, now we have an integral that we know how to do. We know how to do this. We can integrate a square root, right? We've done that. So this is going to equal 2/3 u to the 3/2 plus c. All right, one issue, though, is that we want our answer in terms of x, not u. Because the original problem was definitely in terms of x, and if you have a problem in terms of x, you want an answer in terms of x. So I can't just say 2/3 u to the 3/2 plus c. So what can we do? Above, we said that u is 1 plus x squared. So we can put that back into the answer, and then we'll have an answer in terms of x. So let me put this in parentheses. And what we wrote above is 2/3 1 plus x squared to the 3/2 plus c. And that is the answer. So there we go. We've got the problem up top, and this is the entire trick that we used to find the answer. All right, so I'm going to move the page up. So this trick or this strategy seems like it worked, but let's check. Remember, since the indefinite integral is an antiderivative, we can check our answer by taking the derivative of it. So take the derivative of our answer. You know, I've mentioned this before that you can check your answer this way. We don't always do it, though. But I want to check this one. What would I have to do to differentiate this one? We have to use the chain rule, right? Use the chain rule. The 3/2 is going to come down, get multiplied by the 2/3 that's already there. 1 plus x squared, decrease the exponent by 1, times the derivative of the inside function. And the derivative of plus c is just 0. So We used the chain rule. And then we could just try to simplify this. 3/2 times 2/3 is 1. And yeah, we get 2x square root 1 plus x squared. And that equals the original function that we were integrating. So I'll just put a little check mark next to this. Yes, I checked my answer, and it checks out. Derivative of my answer equals the original function. You know how I said a few minutes ago that it felt like we needed something that was going to be like the chain rule, but in reverse? We did this trick, we got our answer, and in order to check our answer, we had to use the chain rule. So that kind of makes sense. All right, now this trick that we talked about, it's more than just a trick, and this is called the substitution rule. So let's state it formally, and then we'll see it on some other examples. Now, let me just tell you, I'm going to write this as a sentence, but I don't really think of the substitution rule as a formula. I don't think of it as a formula. I think of it as a strategy. So even though we need to write this, well, let's just see. If this is a differentiable function, then the integral of f of g of x times g prime of x dx equals the integral of f of u du. So it almost looks like a chain rule thing is showing up in that formula. You don't need to memorize this formula. That's not what this is about. We'll just do problems and understand this as a strategy. But still, this is just a more formal way of saying what we did above, just so you can see that connection. In our example above, f of u was the square root of u, and g of x was 1 plus x squared. And then if you put this all together, you'll see that it's basically the left-hand side is a complicated integral in terms of x, and we turn it into a simple integral in terms of u. And that's what we did. And I'm saying that, in a sense, the substitution rule is a little bit like the inverse of the chain rule. Now, let's do some other problems, because we just talked about this one problem. So I want to show you some other ones. Using this strategy to answer questions that we couldn't do until now. So, for example, let's say we want to find the integral of 3e raised to the 3x plus 1 dx. All right, I'm going to do this for us. If you think about what we did in the previous one, I said the trick is to introduce a new variable called u. And we did that by letting u equal part of the original problem. So we're going to do that again. We're going to let u equal some part of this. The part of this that I'm going to let it equal is 3x plus 1. Okay, so if I do that, and then I do d dx of both sides, du dx equals just 3, right? And then bring the dx over to the other side, du equals 3 dx. Then the original problem that we had, 3e to the 3x plus 1 dx, I look at the original problem and I say, this is kind of like e to the u. But not only that, we have a 3 and we have a dx, so I'm going to put the 3 and the dx next to each other. because then that part is going to become du. And this part is going to become e to the u. So what we're doing here is we're taking a complicated problem in terms of x, turning it into a simple problem in terms of u. We'll be able to finish it from here. We know the integral of e to the x is e to the x, so the integral of e to the u is e to the u plus c. And then we say, all right, well, remember, we need to get the answer back in terms of x. But at this point in the problem, you'll always have something already on your page that will help you translate it back into terms of x. In this problem, we have u equals 3x plus 1. So that's what I'm going to substitute back in. 3x plus 1. And now my answer is in terms of x. So that is the substitution rule. That's the strategy. We have to talk about this a little more. I mean, you can see there's much more to this lesson, but let's talk about what we've done so far. All right, we started by letting u equal part of the original problem. That's the next thing I want to talk about, is how did I know which part of the problem to let u equal? We'll talk about that in a moment. But I also want to say that once we had u, we did du dx, and then we split up the du and the dx. From now on, I'm usually not going to write this middle step here. In fact, you know what? I'm going to put it in parentheses. This. We can do this part in our head. We could just kind of go from u equals 3x plus 1 to this. That's usually what I'm going to do, and not write the part in parentheses. Because I could say, all right, the derivative of 3x plus 1 is 3, and let's write 3 dx. Okay? So in future problems, I'll go from this to this. Now, then we took the original problem. I like to do this step of rearranging the original problem. Like, I put the 3 and the dx next to each other because 3 dx is du. And I like to write it underneath like that. I mean, you don't necessarily have to write it exactly how I do. But yeah, this is showing me what part I'm going to substitute u in here. I'm going to substitute du here. And then we have an easier problem. We integrate the easier problem, and then we turn it back into terms of x. You could check your answer, take the derivative of your answer. You'll probably need to use the chain rule and make sure it equals the original problem. But checking your answer is optional. Now, note, one challenge is deciding what to let u equal. You know, because both of these problems, I started off by saying let u equal this. And you might say, like, well, how did I know to do that? The answer is we often want u to be the inner function. And that could be something inside parentheses, under a square root, or in an exponent. And I guess in the two problems that we did, that's how I chose u. I mean, in the first one, I let u equal something that was under a square root. And in the second problem here, I let u equal the thing that was up in the exponent. So that seems like that worked out. But really, if you think about it, why does it work out? It works out because the u that we chose is easy to differentiate But not only that, the u that we chose, its derivative appears in the original problem. That's important. Like, the derivative of 3x plus 1 is 3. And a 3 appears in the original problem. So that's what makes this work out. So you look for something that is probably an inner function. But not only that, its derivative appears, and that's what's going to make this substitution work out. One other thing I want to mention before we move on, notice that we have the problem entirely in terms of x, entirely in terms of x, and then entirely in terms of u. At no step in this process do I have an expression with x's and u's at the same time. Like, I don't have a 3x plus 1 and then a du. Like, don't do that. Don't mix x's and u's in the same expression. It's all in terms of x, and then it's all in terms of u. And then the answer is all in terms of x. We're translating back and forth between the two. Let me say that if your choice of u doesn't get you anywhere, then start over with a new one. I'll say with a different one. Basically, I'm saying that deciding what to let u equal is a challenge in some problems, because you might get a problem that looks like it has two different inner functions, and then you have to decide, like, well, which one is going to be u and which one is not. Or you might get a problem that doesn't have any parentheses or square roots or exponents, and it still could be a substitution rule problem. So if you try something for u and it doesn't seem to be working, you can't really force it to work. If it's the wrong choice of u, it's just not going to work, and you need to take a step back and start over with a different choice. So let's look at some other problems, and now maybe they'll gradually start to become harder problems. All right, I think I'm still going to do these two for us. I'll have some other ones for you to try a little bit later. All right, that's going to be part A. There's also a part B. E to the x, e to the e to the x. I'll let you see those, but I think I'm going to do these for us. If you really want to, you could pause and try these. It's up to you. All right, let's work on part A. So, I mean, maybe first you take a quick look and say, can you solve it without the substitution rule? Can you do this just with the tricks, you know, the strategies from a few lessons ago? I don't think we can. I think this is going to need the substitution rule. But what should we let u equal, right? There's something in parentheses, and there's something under a square root. And the answer is one of them is going to work, and one of them is not. You know, one of the choices of u is the correct one. So let's just mentally check. If I let u equal 2x plus 1, what's going to happen? If u is this, then du is going to be 2dx. This problem doesn't have a 2dx in it. In fact, it has all this other stuff. So let's put that on hold for a second, and let's imagine, what if we let u equal the part that's under the square root symbol, not including the square root, just the stuff that's under the square root, x squared plus x. If that's u, then du is going to be 2x plus 1 dx. That's going to work out great. So let's do that. Let's let u equal this. Because then du is 2x plus 1. I should have a dx here, right? But before I write dx, keep in mind, I want 2x plus 1. I want all of this to get multiplied by dx. So let's put parentheses. You put parentheses around things in math when you want to group them together. So we want to make sure all of 2x plus 1 is getting multiplied by dx, not just the 1. This is good. This is great because look at this. The problem that we have, I'll do my thing where I rewrite it. Sometimes I like to do this to put the part next to dx that kind of goes with it. This is going to be du. And if that's du, what's the rest of it? Square root of u. So we've turned this problem into a much simpler problem in terms of u. In fact, we turned it into a problem that we've already done earlier. We did the square root, we did integral of the square root of u du. We got 2/3 u to the 3/2 plus c. So are we going to get the exact same answer as that other problem? Well, not really, because once we get it back in terms of x, it's going to look different. This is 2/3 times x squared plus x to the 3/2 plus c. So part of the problem looks like the one we did earlier, but the final answer is different. So that was part A. Let's look at this function that I wrote for part B. E to the x, e to the e to the x. That's interesting. I don't even know what that function would look like if we were to graph it. It's kind of unusual. How are we going to integrate it? Well, substitution rule. Let's let u equal something. Now, we want u to be something that's easy to differentiate. And when we differentiate it, we want the derivative to be something that appears in the original problem. So how about this? I said in my kind of guidelines above that we often want u to be something that's inside parentheses, under a square root, or in an exponent. We have x appearing in an exponent, so I could try to let u equal x. But I don't think that's going to do much. If we just let u equal x, you know, the derivative would be 1. I don't think that's going to help. How about this? E to the x. E to the x appears in an exponent. So let's try this. All right, then du is e to the x dx. So the problem that we're working on, e to the x, e to the e to the x. If we rearrange it a little bit, looks like this. And sure enough, this part is going to be du. What's this part? E to the x can be thought of as e to the u. Pretty cool. So this entire problem turns into one that's much easier. It's great in math when we can take a complicated problem and turn it into an easier problem, and then solve the easier problem. And then maybe we have to convert the answer back into the original variable. So we need to get this back in terms of x. U was e to the x, so we get e to the x plus c. Make sure the plus c is all the way down there. The plus c is not in the exponent. And yeah, you could check your answer, you know, take the derivative of this. You'd have to use the chain rule. Looks like it would work out. So we've seen a few problems. We've talked about how to select what u should equal. There's another thing that can come up that I need to tell you about. And that is sometimes du must be multiplied by a constant. I'll show you what I mean. This is going to be another substitution rule problem. All right. What do I mean? Sometimes du must be multiplied by a constant. Well, let's look at this and say I can't really do this using methods from, the previous lessons. So we'll try the substitution rule, and we should let u equal the inner function, 2x plus 1. Well, then du is 2dx. All right, here's what's happening differently in this problem is we don't have 2dx in the original problem. All the problems that we've done so far today, they always worked out where when we found du, it always equaled something that was in the original problem exactly. And you might say that that was actually really convenient, the way that a lot of those problems worked out. Before we continue, let me just quickly show you something. When we did this one earlier, and we found du was 3dx, wasn't it really convenient that there was a 3 here? Because the 3dx was in the original problem. And then when we did this one here, wasn't it really convenient that when we did the derivative of x squared plus x, that it equaled 2x plus 1, which just coincidentally happens to be here in the original problem? So, yeah, it's true that some of these problems are set up to be convenient on purpose. This one is a little bit less convenient. The problem does not have a 2dx. So it only has dx, not 2dx. The problem does have a dx. So here's the idea. Here's what we're going to do. We're going to take this and multiply both sides by the constant 1/2. And that's going to give me 1/2 du equals dx. Yeah, so the reason why I multiplied by 1/2 is because now there's a dx here, which is good because the original problem has a dx. I'm going to underline that this dx matches up with this dx. So in the problem, square root 2x plus 1 dx, we could take dx and replace it with 1/2 du. And then the rest of the problem is the square root of u. So you see the problem was kind of off by a factor of 2, and we're fixing it by multiplying by 1/2. Really, that 1/2, here, it's going to look like this, right? Square root of u times 1/2 du. But that 1/2 is just a constant, so we could pull it all the way out. That's probably what we should do if we're going to integrate. Just pull a constant out front. So when I say sometimes du must be multiplied by a constant, in this case it was 1/2. In some other problem, it might be 1/3. In some other problem, it might be -2. Whatever you have to multiply by in order to make it work. But if the substitution rule is going to work, it can only be off by a constant. It's never going to be off by like x or x squared or anything like that. Just constant, it might be a fraction. All right, so we get 1/2 times 2/3 u to the 3/2 plus c. And then we have to multiply the 1/2 times 2/3 to get 1/3. And let's get this back into terms of x. 2x plus 1 to the 3/2 plus c. All right, so now we've really seen how to do this, and we've seen that sometimes it's off by a constant. So I want to give you some problems to try. Let's do a fresh sheet of paper, and I'll give you 2 problems to try. All right. I'm gonna give you 2 of them. Okay, so I'd like you to pause the video and try these out. So, looking at this, I'm thinking we should let u equal 5x plus 1. If we let u equal 5x plus 1, that's going to be nice because du equals 5 dx. And then the problem has a 5 dx in it. So yeah, this is one of those convenient ones where the 5 dx can be replaced with du. And then what's the rest of it? 5x plus 1 to the 15. That's going to be u to the 15. We can do that integral. That's easier than the original problem. I guess this turns this into just u to the 15 du. And we know that that equals u to the 16 over 16 plus c. And then we need to get the answer in terms of x. So instead of u, it's going to be 5x plus 1 to the 16. All of that over 16 with a plus c on the outside. For the second one, we have to figure out, what are we going to let u equal? And I think you look at this and you might see more than one choice, but the best choice is going to be the thing that's up there in the exponent, the x cubed minus 1. Because then du is 3x squared dx. And yes, that appears in the original problem. The original problem can be thought of like this, which means this piece of it will become du. And for this piece, we'll substitute in e to the u. So it seems like we've had a few problems today that kind of simplify to the same integral of e to the u du. And we also had a couple of problems that became the integral of the square root of u. So you see some of the same integrals come up again and again. But the final answer will still be different once it's in terms of x. So this is going to be e to the x cubed minus 1. Make sure that's in the exponent, and make sure the plus c is not in the exponent. Plus c should always be on the outside. Tell you what, let me give you one more. I'd like you to try one more. This is going to be the integral of 1 over 8x minus 3 dx. So this is another where you could pause the video and try it out. Okay, I think this one is a little bit different than the other ones. We can't really do this without the substitution rule. We basically need to let u equal something. Now, you know how I said that often we let u equal something that's in under a square root or in parentheses or up in an exponent. This problem doesn't have any of that. It doesn't have any of those things. So, should we let u equal 8x? Should we let u equal 1? Should we let u equal 8x minus 3? You might have to do a little trial and error until you get used to these problems and kind of see patterns of what works. The 8x minus 3 is going to wind up being the best choice. It appears in the denominator. And du is 8dx. And you say, the original problem does not have an 8dx. Actually, it would be really convenient if the numerator had an 8 in it, right? If the numerator was 8, then yeah, we would have 8dx, and that would be great. But we don't, so what I'm going to do is multiply both sides of this by 1/8. Because the original problem does have a dx. So that dx is going to become 1/8 du. Let's continue this over here then. How about we write it like this, where the dx is going to become 1/8 du, and the 1 over 8x minus 3 is going to be 1 over u. So you see, we are getting the problem entirely in terms of u. We could pull the 1/8 out. It's just a constant, and we have 1 over u du. So you should remember what this integral is. This is going to be 1/8 ln absolute value of u plus c. And then we need to get the answer back into terms of x. So we do 1/8 ln absolute value 8x minus 3 plus c. Make sure you have the absolute value there. Okay, there you go. So that one was a little bit trickier because it had that step where we had to multiply by a constant, but it's really just one extra step. All right, so you just did a few problems. I think I have another one I want to show you. So I'll do the next one. The next one is interesting because it might surprise you that it's a substitution rule problem. Let's say we want to compute the integral of tan x dx. Yeah, so I'll do this. Well, a couple of lessons ago when we first learned about the indefinite integral, we talked about what's the indefinite integral of sine x, what's the indefinite integral of cosine x. But we did not talk about tangent. We haven't learned what the integral of tangent is. Now, if you think about it in terms of being like an antiderivative, you might say, do we know a function? Have we seen a function this semester that when you differentiate it, the result is tangent? And I don't think we have. I don't think we've seen that. So here's an idea. Okay, first thing I'm going to do is I'm going to rewrite it as sine x over cosine x dx. A lot of times in trig, when we're stuck with a tangent or a cotangent or something like that, getting it in terms of sine and cosine sometimes helps. We can't just integrate the top and integrate the bottom. That doesn't work. We've never said that that's a rule. Like, we've never said you can just integrate the top and bottom. So it feels like we need something kind of like the quotient rule, but for integrals, and we don't really have anything like that. So let's try to use the substitution rule. But what should we let u equal? Should we let u equal the numerator? Should we let u equal the denominator? They seem like they are equally valid choices. for what u should be. So what I'm going to suggest is let's see what happens with each one. If we let u equal sine x, what's going to happen? Du is going to be cosine x dx. Does the original problem have a cosine x dx? No, it actually doesn't. That's what's tricky about this. You see cosine x, you see dx, but the cosine x is on the bottom, right? This is like a 1 over cosine x. So no, not really. We don't have a cosine x times dx. I'm going to say this is not helpful. If the cosine was like up top, maybe that would be a different story. So what if we try u equals cosine x instead? Let's see if this is helpful. Then du is negative sine x dx. Does the original problem have negative sine x dx? Almost. It almost does, right? It has a sine x dx. So this is better. This is a better choice. In fact, we can make this work exactly if we multiply both of these sides by a constant, in particular, the constant -1. All right, so now we have a sine x dx, and the original problem has a sine x dx. So we will be able to finish this using the substitution rule. Let's see. All right, so I'm thinking of the problem as the sine x dx is one part, so let's kind of rewrite it as 1 over cosine x times sine x dx. That's the part that I wanted to replace with, I guess, negative du. And then what's the rest of it? 1 over cosine x is 1 over u, because we used this. We used this. You could even cross out the other one. We wound up not using the other one. All right, so the problem becomes the negative du is like -1 times du, and you can just pull the minus all the way out. So minus integral 1 over u du. When you integrate it, you get negative ln, absolute value of u, plus c. The plus c is on the outside. Try to get the answer back in terms of x, and you get negative ln, absolute value, cosine x, plus c. So, believe it or not, that is the integral of tangent x. Technically, I guess you could check it by finding the derivative. There's two things I want to say about this before we move on. First thing I want to say is that you could use a similar strategy to find the integral of cotangent x. So if you ever had to find an integral of cotangent x, cotangent is just the reciprocal of this, so cosine on top, and it would work out. Another thing I wanted to say about this is if you ever look up the integral of tangent x, you might see it written this way, or there's another way that you could write this answer. So I wanted to mention sometimes it's written as ln absolute value secant x plus c. And these are equivalent answers. Can you see why these answers are equivalent? It's because when you have a constant in front of a logarithm, like a -1, it can be brought inside as an exponent. And then cosine x raised to the -1 is the reciprocal of cosine, which is also known as secant. So these are equivalent to each other. If you ever look it up and you see something and you're like, why doesn't that agree with what I found? They actually do agree. They just look different. So we've talked about the substitution rule. We know how to do this for actually a lot of problems now. I feel like you could answer a lot of different problems. But so far, everything that we've done in this lesson has been the substitution rule on indefinite integrals. And we need to talk about the substitution rule for the other kind of integral, definite integrals. Definite integrals, you know, when you have a lower limit of integration and an upper limit of integration, what do we do then? So there's kind of two different methods. I'm hesitant to actually call these two different methods because they're really equivalent to each other. I'm going to say it's going to be your choice. Maybe these are just two different approaches of how you're going to write it. They're going to be the same amount of work either way. So earlier we stated the official rule, like the official substitution rule, had a formula. So I want to tell you that for definite integrals, we can also write it as a formula. Even though I think for actual problem solving, we're just going to treat it as a strategy. So don't worry about memorizing this. But if you want to see precisely how this works, this is how it's going to work. So method 1 is to take the formula from the substitution rule and just put the a and the b on it, and then say put the brackets around it and put the a and the b there. Method 2 is going to say, start with the same type of problem, so same type of left-hand side. The right-hand side is going to be treated differently. We're actually going to write g of a, g of b, f of u du. So let me explain what these mean. Method 1 says drop the limits of integration do what we did for indefinite integrals, and then evaluate at a and b, or, you know, I guess I'll say b and a, subtract. All right, let me explain. So the formula that appears on the left-hand side, it also appears on the right-hand side, but we dropped the limits of integration. They're not there. So now it looks like an indefinite integral. So we do what we did for indefinite integrals, which we've been doing this entire lesson. We get an answer. We get it in terms of x. And then you deal with what's outside of the brackets, which is the b and the a. So you get your answer in terms of x. You evaluate it at b, you evaluate it at a, and you subtract. So that's one way to do these. Method 2 says keep the limits of integration. Keep the limits of integration, but adjust them accordingly. So you see what I wrote for method 2, both of the integral signs on the left and on the right, they have limits of integration. There's a number on the bottom, there's a number on the top, but it's not the same number. It's not a and b anymore. Instead of a and b, it's g of a, g of b, where g is that inner function. G is the thing that we've been calling u. So we'll do a problem with this, and I think what I'm going to do is I'm going to show you a problem and I'm going to show you both methods, and then maybe it'll be clear and you can decide which method you prefer. If I show you one problem with both methods, of course, we're going to get the same answer, but you could see and decide, you know, which perspective do you prefer. So let's do one that we haven't done yet. Actually, it has to be a problem we haven't done yet because we haven't done any definite integrals. So we're going to do from 0 to 4 square root 2x plus 1 dx. And first, I'm going to show you method 1. So did we do part of this problem earlier? I think we did. We did this, but without the 0 and the 4. Okay. So what method 1 says is you could put brackets around the whole problem, drop the limits of integration. There are no limits of integration right now, but the 4 and the 0 are on the outside. Order of operations says we should do what's inside the brackets first, save the 4 and the 0 for later. So we would do what we did earlier on this problem and just like ignore the 4 and the 0 and just treat this like the problem we did earlier. We showed some steps for it earlier, and I think we got 1/3 2x plus 1, the 3/2, and the 4 and the 0 are still out there. Oh, you know what else? You know what else I should say? We don't need to write the plus c. We don't need to write the plus c in here. Just like other problems that we've done with, you know, the evaluation theorem, you don't need a plus c inside, because if you put a plus c there, it would wind up canceling out by the end anyway. You'd get a c minus c. All right. Also, we know that the answer to this is just going to be a number. So what do we do now? We just evaluate at 4, evaluate at 0, and have subtraction. So 1/3, 2 times 4 plus 1 to the 3/2 minus 1/3, 2 times 0 plus 1 to the 3/2. So we put in the 4 and we put in the 0. Hopefully this simplifies to a nice, neat number. All right, first things first, this is 9. And this is 1. So yeah, we can work with this. 9 to the 3/2, you could do a little scratch work off to the side if you need to, but you should find that you get 27 over 3 minus 1 over 3. So final answer of 26 over 3. So that's method 1, but it seems like I left out some steps. So let me just point out that we did this earlier. So those are the steps that I left out, the ones that we already did. Let's look at this problem with method 2, and then you could decide which method you prefer. I think method 1, you know, it worked out. We have the brackets on the outside, and we could just do this like all the problems we've been doing today, but then the 4 and the 0 are there to go in towards the end of the problem. 4 went in and the 0 went in. Okay, same problem. I know the answer is going to be the same, but let's try out this other method for size and see what we think of it. This time, in method 1, I kind of left out the steps that we did earlier. This time, I think I'm going to show them. What we did earlier was we let u equal 2x plus 1, and we said that du is 2dx. Remember this? And then we said, wait a second, the problem doesn't have a 2dx. It only has 1dx. So we multiplied both sides of this by 1/2. It was one of those problems. Okay, so I'll kind of just section this off. So the problem then, 0 to 4, square root of 2x plus 1 dx. I'm thinking that the dx is going to get replaced with 1/2 du. The 2x plus 1 square root here is going to get replaced with square root of u. The 1/2 can get pulled out front. Integral sign. Square root of u, du. But there's something we need to do here. We need a number to go up here, and we need a number to go down here. When I wrote method 2 above, I wrote these numbers as g of a and g of b. So what is g? Like, what is this function g? Well, this is g. This is the g that we chose for this problem, 2x plus 1. So g of 0 and g of 4 would mean, here's how I'll write this. I'm going to say, when x equals 0, what does u equal? If x is 0, because these were x values, right? 0 and 4, those were x values. I want to turn them into u values. So when x is 0, u is 2 times 0 plus 1, which is 1. So we put a 1 here. Up here, when x is 4, then u is 2 times 4 plus 1 is 2 times 4 is 8, plus 1 is 9. So this is going to become a 9. This is what I meant when I say we keep the limits of integration, but we adjust them. So the 0 and the 4, those were x values, and we wanted to turn them into u values. So the 0 got adjusted to a 1, and the 4 got adjusted to a 9, because when you put in 0 and 4 into this, you get 1 and 9. Now we can continue the problem from here, and what's actually nice about this method, like that seemed like some extra work that we had to think about. But what's nice about this method is we don't actually have to convert it into terms of x. We can get 2/3 u to the 3/2. I'm not going to write the plus c. 9 and 1. We can just finish it from here. We don't actually have to get it back in terms of x, because ultimately it's just the answer is just gonna be a number anyway. So this is 1/2 times 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. And if you work this all out, you do get 26/3. So which of these two methods do you prefer? I would say that they are about the same amount of work. This is one of those cases where I think that I might use one method or the other depending on the problem. But I probably lean more towards method 1. I probably use method 1 a little bit more often. Okay, I'm going to give you a problem to try. It's going to be a definite integral, and you'll decide if you want to use method 1 or method 2. And you don't have to do it both ways, you know? That was just to demonstrate. So I'd like you to try to integrate e to the 3x dx from 0 to ln2. So you could pause the video and try this. All right, so I don't know if we're thinking method 1 or method 2. On my paper, I actually did this both ways, but, you know, you can choose one way or the other. Let's start by figuring out what substitution we're going to make. So let's let u equal 3x, because that appears in an exponent, and it's kind of an inner function, and it's easy to differentiate. We get 3dx. The original problem has dx. It doesn't have 3dx. So I'm going to multiply both sides by 1/3. And sometimes I section this off. That's the substitution that we're going to use for this problem. So I think I'll use method 1. And say that this problem can be viewed as big brackets around it, drop the limits of integration, e to the 3x dx, and now the ln2 and the 0 go on the outside, ln2 and 0. And the substitution that we're making, you know, I often like to label it underneath and say this is going to become 1/3 du, this is going to become e to the u. So where does this get us? Let's put the big brackets around it. We could pull the 1/3 out, I guess. Like 1/3 integral e to the u du. There's something a little different I'm going to do here that I haven't told you about. You know the ln2 and the 0? You know how if we're doing method 1, we keep, we keep those limits of integration on the outside? We dropped them from the inside. Well, what I'm looking at here is ln2 and 0, those are basically x values, right? We're integrating from x equals 0 to x equals ln2. But at this step in the problem, we've converted the problem from a problem in terms of x to a problem in terms of u. If we were doing method 2, we would adjust the limits of integration, but I'm not going to do that. There's still going to be ln2 and 0. But what I'm going to do, just to make it extra clear that these are x values, I'm going to write x equals ln2, x equals 0. That's a nice thing to do because it makes it clear that even though what's inside shows u's, we're still thinking of these as x values, and we're not going to plug them in until after we get this back in terms of x, because these are x values. So I think that's a good notation to use. I guess the reason I didn't do it on the previous problem is because on the previous problem I skipped some steps because we had already done them earlier. All right, so what does this get us then? We integrate this, and we get 1/3 e to the u. We don't need to write the plus c. This is still an x value. And now, for the part that's inside the brackets, we need to get it back into terms of x. Well, we said u is 3x, so this is 1/3 e to the 3x. And at this point, I could just write ln2 and 0, because the problem is completely back in terms of x anyway. or you could write x equals. At this point, it doesn't really matter. So 1/3 e to the 3 ln 2 minus 1/3 e to the 0, right? 3 times 0. Okay. I mean, that's 3 times 0. I just wrote 0. So e to the 0 is 1. Let's figure out what this other part is. So how about a little scratch work? All right, e to the 0 is 1. That's not all of the scratch work I wanted to do, but that's part of it. What does the other thing equal? E to the 3 ln 2. What is that going to be? Remember that rule about logarithms, that when you have a 3 outside of a logarithm, you can move it inside as an exponent? Ln 2 to the 3rd. What's 2 to the 3rd? 2 to the 3rd is 8. 2 times 2 times 2. And e to the ln 8 cancels out and just gives us 8. So that was a good little bit of scratch work, because now I see that this is going to be 1/3 e to the ln 8 minus 1/3 times 1. And then this is going to be 1/3 times 8. Oops. 1/3 times 8 minus 1/3. Final answer is 7/3. So we answered the problem. We're done. I think that just because this was a problem that I asked you to try and I told you to choose whichever method you wanted, I think I'm going to show you this with method 2 anyway. Just in case you did it with method 2, or in case you're curious about it, you know, let's look at this problem from that perspective. This is the problem. And we do the same substitution. We let u equal 3x. du is 3 dx, so 1/3 of du is dx. All right, starts off the same. So what I'm thinking here is that this is equal to e to the u times 1/3 du. But let's figure out the new limits of integration, what goes here. We've converted the problem into terms of u, and when x is ln 2, what does u equal? U is 3x, right? U is 3 ln 2. Maybe something that would be nice to do here is, instead of writing it as 3 ln 2, we could write it as ln 2 to the 3 equals ln 8. I think we either have to do this sort of thing now, or if we don't do this now, we're just going to wind up doing it later anyway. So I'm just going to do it now and say this is ln 8. For the other one, when x equals 0, u is 3 times 0, which is 0. So actually, the 0 didn't change for this one. So now we continue the problem from here. I'd probably pull the 1/3 out. Actually, let's just integrate it. 1/3 integral of e to the u du is e to the u. And I can write ln 8, and I can write 0. And I don't have to write x equals or u equals or anything like that. These are u values. ln 8 is already converted into a u value. So in the next step, I'm going to put ln 8 in for u and get e to the ln 8 minus e to the 0. This kind of looks a little different than the way the problem was kind of ending previously, but it's going to work out to be the same. So this is 1/3 times 8 minus 1. So we do get 7/3. So I think that the two methods take about the same amount of work. I said that I kind of lean towards preferring method 1, but it's up to you which one of these you like. All right, so I know this has been kind of a longer lesson, but I think we're going to wrap things up here. So that's the substitution rule. It was kind of a longer lesson because we needed to talk about using the substitution rule on indefinite integrals and also definite integrals, and that's kind of why it's almost like 2 lessons in one. But anyway, I mentioned at some point earlier that there are also other rules for integrals, but you don't see some of those until Calculus 2. So that's okay. Substitution rule is going to allow us to integrate a lot of problems, and there's still some problems that just don't show up in Calculus 1. They get saved for Calculus 2. So, just so that you know, Calc 2 actually does pick up right where Calc 1 leaves off and continues integration. Let's see, what else? So we're almost at the end of Calc 1. Next time, we're going to talk about area between two curves. So we're going to get back to talking about area, maybe drawing some pictures and shading in some regions. All right, so that's it for today, and I'll see you soon.